Okay, wonderful.
All right, we are recording. Well, thank you so much to Zoë Kitchel for joining us today from Rutgers University, where she is studying. This is in the context of the geographies of risk work. She and I spoke for a podcast episode about bringing geographies of risk into sort of marine spatial ecology, and which is an interesting place to think about it, and it has to do with this intersection between sort of climate change, the effects of climate change on natural systems, but also in this case the implications for fisheries and sort of the economies around those fisheries that are intimately connected to what these marine species are doing in response to climate drivers. So, Zoe, thank you so much for joining us today, and we look forward to your talk.
Absolutely. Thank you so much for inviting me and also allowing me to be a part of the podcast as a part of this really exciting and really timely Geographies of Risk seminar series. And I always start talks by saying this, especially virtually, but if at any point it seems like my audio is not working or my video is not working, or perhaps my slides are not progressing, anyone feel free to speak up and let me know. I want to make sure that I'm able to communicate as effectively as possible. Through this talk, I hope to convince you of three things. One, species are moving in the ocean, although not necessarily always in ways that we would predict. Two, these movements have far-reaching consequences for humans. And lastly, forward-thinking management can help mitigate many of these consequences associated with species that are on the move. To give you a roadmap of what I am going to talk about today, I'm going to start off by talking about how and why marine organisms are moving where they live in the ocean. We will then consider how these movements are impacting fishers and fishing communities. And then we will end by zooming out a little bit and considering the consequences for international relations. But we'll start on the ecological side, which in many ways is my bread and butter as a marine ecologist. Due to climate change and also land use change and ocean use change, the flora and fauna of the planet are facing unprecedented changes. In response to these changes, in a lot of ways, species have three options. They can adapt in place through evolution or phenotypic plasticity, which refers to instances where the same genetic makeup can produce different outward traits that we see or experience. Alternatively, they can move to a new location. Lastly, although obviously less than ideally, they can go extinct. Today, I'm going to focus on one of these options, changing location. We have abundant evidence that a diverse array of terrestrial, freshwater, and marine organisms are shifting where they live. There are equally interesting stories to be told about movement on land and across freshwater landscapes, but today I'm going to focus on range shifts in the ocean. I'm going to start by introducing you to selfishly, one of my favorite species here on the East Coast of the United States. Black sea bass is a popular recreational and commercial fish species that lives in the northern United States up into Canada. And just to orient you, this map begins in North Carolina in the south and stretches up into the Canadian province of Nova Scotia in the north. The colors on this heat map indicate the likelihood of catching black sea bass in the waters off of these states and provinces. It's a habitat suitability map for black sea bass, specifically for 1972, revealing that because of the habitat conditions in a particular location, we would be more likely to find black sea bass in the red areas, the regions off of the southern regions off the coast of Virginia, Maryland, and Delaware at this point in 1972. But let's just take a moment to watch as this video cycles through this habitat suitability map through the 70s, 80s, 90s, moving into the 2000s, and up until now. Just as a reminder, this is where we started in 1972. And this is where we ended in 2019. Three things that I hope you noticed is that we're more likely to find black sea bass further north over time. But what's interesting to point out is that sea bass are still found off the coast of Virginia, Maryland, and Delaware in the southern areas. What we notice is it's not a consistent range shift over time. There's a lot of stochastic movement that happened in those in-between years between 1972 and 2019. And this is reflective of the fact that range shifts are complicated and dynamic. Well, on average, we can say that black sea bass are moving northward at a rate of approximately 100 kilometers a decade. It's much more difficult to say how the distribution of this fish will change from one year to the next. Range shifts are hard to predict, and they don't always look like how we might expect them to. The story of black sea bass shifting their range towards the poles isn't unique. A number of ecologically and economically important species in the ocean are shifting where they live. American lobster might be familiar to you. It's definitely familiar to Eli and I as both former Maine residents. They are an invertebrate species with huge economic importance to the economies of the northeastern United States and also eastern Canada. Lobster also play an important ecological role as a benthic predator that move energy from the ocean floor up into the water column. Their historic range in the Northwest Atlantic is depicted here in red, while their current range is shown in blue. Similar to the black sea bass, lobster exhibit what we call a range expansion up into these new Canadian territories, but not necessarily a range contraction at the southern boundary. Another example are Humboldt squid, which are currently expanding their range both northward and southward in the Pacific Ocean. These squid are over 6 times larger than the squid that come to market as calamari on our dinner plates. And they have an incredibly voracious appetite, which allows them to grow from about a millimeter long when they're eggs, all the way up to 50 kilograms in less than 2 years. They're really fast growers. And already this species and the expanding range of this species is impacting the hake fishery in Chile. And we're just beginning to understand how it's impacting the West Coast fisheries of North America. Another example specific to the Southern Hemisphere is the cushion star, which is shifting south off the east coast of Tasmania. This sea star is an intertidal species, and although herbivorous, it has a really incredibly large impact on the intertidal landscape in Tasmania. These are just a few examples, but some studies have looked at all the examples that we have information on, and they found, looking at a wide array of marine organisms, that on average, organisms in the ocean are shifting about 6 kilometers per year away from the equator. If we scale this up to a century, that means that species are shifting about 600 kilometers or roughly the distance from Southampton to Glasgow over the course of 100 years. And it's important to note that these researchers also compared the rate of movement that we're seeing in the ocean to the rate that we're seeing on land. And what's really interesting is that marine organisms are actually shifting their ranges 6 times faster than the organisms on land. There are a number of potential hypotheses for why marine organisms seem to be so much better at tracking climate change than their terrestrial cousins. One factor is that marine organisms in general tend to be more sensitive to change. Another factor is the reality that there are just more natural and also man-made barriers to movement on land than there are in the ocean. On land, species have to traverse rivers and agricultural fields and mountains and highways and other obstacles in order to seek more suitable habitat. So my question becomes, what exactly is causing these range shifts? I've mentioned that climate change tells part of the story, but does it tell the whole story? Probably not. But it does tell an important part of the story. The ocean has absorbed 90% of the heat resulting from the buildup of greenhouse gases in our atmosphere. 90%. If we didn't have the ocean, we would not be living on this planet at this point. Subsequently, the average temperature of the global ocean has warmed. We see that what's especially interesting is the way that the ocean is warming is not homogeneous across the surface of the Earth. This map here shows the trend in ocean heat content between the early 90s in contrast to the ocean heat content today. The areas highlighted in red represent areas that are warming rapidly. You actually see on here also a few areas in blue, which tell us that these are actually areas that on average since the early 90s are cooling. It's interesting to see that heterogeneity in the ways that climate change is impacting our oceans. And I want to make sure to highlight these few regions that really stick out as these super red regions, which tell us that they are warming way above the global average for the ocean. Specifically, where I am right now in the Northeast United States, highlighted over here on the right-hand side, oceans are warming about 3 times faster than the global ocean. So about in the past century, they've warmed about 1.5 degrees Celsius. Other regions to note are the Arctic. We hear a lot about this in the news, how quickly the Arctic is warming. It's warming about 2 times faster than the average ocean warming rate. And specifically within the Arctic, the Chugach Sea off the coast of Alaska is warming the fastest. And additionally, these oceans off the coast of Korea, China, and Japan, and specifically the Sea of Japan, is another one of those areas that's warming tremendously quickly. And I encourage you to keep this snapshot in your mind as we continue moving through the talk and start talking specifically about the more human impacts of these range shifts. Marine ecto, the reason we talk about temperature so much when we talk about range shifts is that marine ectotherms are incredibly sensitive to temperature change because they have adapted to centuries and even in some cases millennia of relatively stable thermal conditions. Compared to land, there are fewer thermal refugia in the ocean. Animals in the ocean, they can't fan themselves like maybe an elephant would, or they can't burrow underground like maybe a lizard or a rodent would. It's harder to escape when you're immersed in this water bath. Additionally, because of the high thermal capacity of water, temperatures just don't vary as much over the course of a day or even over the course of a year as they would on land. As air temperature fluctuates, water temperature often stays quite stable. And the reason this matters is because a wide range of physiological processes for these marine ectotherms are inherently linked to these stable temperature conditions that they're used to. And these include metabolism and growth, how these species move around, how they reproduce, just to name a few of the impacts that temperature can have. And our hypothesis that species may be shifting their ranges in response to temperature is at least partially correct. To test this temperature hypothesis, researchers have compared the speed and direction of species range shifts to the speed and direction of temperature conditions. And the term that we use for that movement of temperature conditions is climate velocity. This map shows global isotherms, which are bands of consistent temperatures across the planet. And climate velocity refers to how these isotherms move through space. In the ocean, these isotherms can move north, south, east, west, and they can also move shallower and deeper. Across a range of different organisms that live on the continental shelf regions of North America, what we have found is that most of them do seem to be tracking temperature quite well. The trajectories that their range shifts are making match those that these isotherms are making. And just to give you a bit of a graphical representation, this plot here on the x-axis, that bottom axis, they refer to it as the thermal envelope shift, which is really just a synonym for climate velocity. So what's the direction and what's the speed at which temperature is changing across these marine landscapes? And then on the y-axis is a similar representation, except for how organisms are moving. In general, organism movement tracks the direction of climate velocity. A perfect match would fall along the red one-to-one line. And most of these points, most of these examples of range shifts fall quite close to that line. And similarly, we can look at these patterns not only across latitude, but also across depths. So this is a this figure's nearly the same, except instead of looking at latitudinal shifts, it's looking at depth shifts. And so species that are experiencing unsuitable temperature conditions, they can move latitudinally to a new place, but they can also move deeper into the water column. We found that 75% of species seem to be tracking temperature north and south in a latitudinal way, and about 70% of the species that we looked at were tracking climate within the water profile, so moving shallower or moving deeper depending on ideal temperature conditions. However, what you also notice is that a lot of these examples, so a lot of these points, they don't fall directly on this red one-to-one line. So there's still a lot of variability that we haven't accounted for by only looking at temperature. And much of this variability arises, one, because no two marine organisms are the same. Therefore, they're not going to react the same to these different stressors. And also because temperature is not the only aspect of habitat that these organisms care about. Marine organisms are incredibly diverse in what they look like, in their genetic makeup, and how they move around. This really beautiful phylogenetic tree from a really awesome website I recommend you explore, fishtreeoflife.org, is really only a snapshot of the marine ectotherms in the ocean. These are just looking at the diversity of fish. But marine invertebrates bring even more immense diversity into these studies of range shifts over time. Those are our crabs and our squid and our sea cucumbers and urchins. Characteristics of species such as body size, age at maturity, movement, how they get around, how they reproduce, how long they live, and how much time there is between different generations, what they eat, what types of habitat they prefer, and also how big of a territory they cover can all influence how these species respond to habitat change. To illustrate the important role of traits in shaping marine range shifts, let's quickly zoom into Oceania, where landscapes are changing rapidly. Since the 60s, charismatic kelp forests in this region, like the one you see here, have declined by over 90%, which is a direct but also an indirect consequence of climate change. Directly, kelp prefers cooler waters and therefore does not do well when the water is warming. But also indirectly, warming waters have boosted the populations of sea urchins, which make it even harder for kelp to tolerate warming as these sea urchins are munching on their bodies. And Oceania isn't the only site of this type of landscape transition. We're seeing similar patterns worldwide off the coast of California, also off the coast of Japan. What we see now is the endpoint of these transitions that we're seeing. Former kelp forests are transforming into these barren, sea urchin dominated and also microalgae dominated landscapes. And one of the areas we're seeing this landscape transition that we typically call tropicalization, as these ecosystems transition from more temperate affiliated kelp species to more tropical associated species, is off the coast of Australia in Tasmania, which has also non-coincidentally experienced significant warming events over the past century. The color map adjacent to the map of Australia and Tasmania shows the latitudinal changes in mean annual temperature isotherms over the study period. So again, we're returning to this idea of climate velocity. How has the location where you might expect to experience 25 degrees Celsius changed over time, moving from 1945 to 2005? And these solid lines you see represent poleward range boundary shifts of coastal marine fishes and invertebrates. So how is that maximum latitude in the southern hemisphere for these species changing over time? And in addition to looking at temperature change, these researchers also considered a diverse array of traits as predictors of how these different marine fish and invertebrates are moving over time. They found that swimming ability, omnivory, meaning they can eat a variety of different things, and also large range sizes, large territories, all had positive relationships with range extension rate, which supports this hypothesis that increased dispersal capacity, your ability to move further, and also your ability to tolerate more types of conditions make it easier for you to track climate change. And these patterns, they don't only apply to marine species, although that's what I'm highlighting today, but also we see similar patterns in terrestrial species. I said earlier that some of the variability in how these marine organisms are responding to climate is due to this inherent diversity across species, as this study gives evidence for. But additionally, some of the variability is also linked to the fact that marine organisms are not only sensitive to temperature. Just as one example, organisms in the ocean, much like us, are also very sensitive to oxygen availability, which is changing globally similarly to temperature. First, in offshore habitats, we are seeing an expansion of what we call the oxygen minimum zone. That refers to the fact that at intermediate depths in the ocean, the ocean in these areas is characterized by low amounts of oxygen. However, as the ocean warms, warm water by nature holds less oxygen, and therefore these oxygen minimum zones are increasing in size. The oxygen minimum zone of the Pacific Ocean near the equator is represented in this heat map figure here. As you move further as you move deeper into the water column, you hit this dark blue area, which is representative of the oxygen minimum zone. Between 1960 and 2008, that oxygen minimum zone expands tremendously, which has consequences for species trying to move around through the water column and trying to find places with ample oxygen to support growth. And at the same time, in nearshore habitats, an influx of fertilizer and other types of pollutants from runoff are boosting algal growth within these nearshore environments. And similar to the oxygen minimum zone, what happens as we boost algal growth is that also boosts bacterial growth as that algae dies. Bacteria, much like us, consume oxygen. And so in areas where we have high nearshore coastal pollution, we're also experiencing a different type of oxygen minimum zone associated with coastal environments. I've focused on oxygen and temperature just because they are two biggies when we talk about species shifting ranges and what they consider as they move around the ocean. But marine organisms will also shift where they live in response to acidification, in response to other types of pollution like microplastics, and also changes in salinity that might be associated with storm events. But it's not just the chemical and the physical characteristics of the habitat that matter in determining how these species are moving through space. Species will also move in response to interactions with other organisms. Marine ecosystems like this coral reef system here are complex, multidimensional systems with a range of players that all have the potential to maintain or perturb these balances. And what the second half of the talk is also going to segue into is this reality that humans are also an important part of this complex, multidimensional marine system. Let's quickly return to the story of the American lobster. And this is one of many examples where temperature is likely an important driver in the range shift that we're seeing, but it doesn't tell the whole story. There are two other important characters that have to be introduced to better understand how lobsters are shifting their ranges. First is the Atlantic cod, charismatic cod. And second are fishers in the Northeast United States. This story of biotic interactions will act as a segue as we continue to think critically about the complex interactions between human action and these species range shifts, and also the feedbacks that are involved as well. The abundance of Atlantic cod near the coast of the United States has declined in recent history. This graph highlights the decreasing trend in spawning stock biomass, which is in reference to the fish that actually contribute to creating the next generation of fish, so the reproducing adults, from 1978 until 2011. And it focuses on the population in one popular fishing region called Georges Banks, highlighted on the map here off the coast of Massachusetts, Maine, Nova Scotia, right on the outer edge of the Gulf of Maine. And in truth, the pattern that we see here in the declining biomass, it started long before the 1970s. Cod have been intensely harvested off the coast of this region for centuries. Just to give you a sense of the economic and also cultural importance of the species in this region of the world, the arm that sticks out here, some of you may have been here. It's a popular vacation destination known as Cape Cod. No coincidence that cod is in the name. And also, if you ever take a visit to the Massachusetts State House, there is a giant cod on the wall and just a centerpiece of that place of both political and economic control over that area. And the story is actually quite similar for the Canadian Maritimes, and cod being a economic but also really culturally rich part of that regional history. And despite efforts to rebuild these cod populations, the species unfortunately is still considered to be overfished and far below what we'd want to see that population size be. But returning to the lobster, in parallel to this decrease in cod abundance, there's been a rapid rise in lobster abundance in the same area. Here we see landings, or the lobster that are actually caught at sea and make it to shore to sell, between 1982 up into 2018. If you think back to the graph that we just saw for cod, what we're seeing here with the lobster is essentially the inverse. This rise in lobster populations in the same area can be partially explained by temperature, absolutely, but it doesn't exclude the fact that the decrease in cod, which are an apex predator in these oceans, has also impacted the population of lobster, allowing them to really blossom because there are no top predators that are feeding in lobster in this area. So we have rising fishing pressure, especially in response to the advent of industrial fishing in the early 20th century. And this has led to a severe decline in Atlantic cod in this region, which subsequently has allowed the also important commercially and culturally American lobster to really benefit from this predator release. And we'll now start to consider what are the implications of these imbalances in the food web on those people that depend on this balance for livelihoods, for food, for economic stability. As ranges of commercially important marine species are shifting, fishers, fisheries managers, policymakers, military leaders, they're having to make these really difficult decisions that are climate related, but then also related to the way that we break up this world into independent nations and states and provinces. Some of the difficult questions that fishers are asking, should I travel further to target the same species? Should I buy new gear or even buy a new boat in order to catch a new species that's moving into this area that I already live? Or is this it? Am I out of the game? Should I leave fishing altogether? And very similarly to how fish vary in their response to climate by inherent characteristics such as body size or diet, we expect that fishers will respond to changing fishing landscapes in line with community and individual traits. Starting with individual traits, some collaborators of mine assessed patterns in fishing locations over time in the Northwest Atlantic. They found really distinctive community level changes in fishing patterns since the mid-90s. Southern fleets of ships, especially of larger vessels, are starting to fish up to 400 kilometers further north than they have in the past. Both of these maps show the trajectory of North Carolina in the south and Maine fishing fleets, and how their destinations to catch fish have changed between the 90s until today. The map on the left, though, specifically represents the path of large vessels over 65 or so feet. Large vessels that are originating in North Carolina from 1996 up until 2014 are going further and further and further north in order to fish. Those vessels in Portland of the same size, they don't seem to be going very far at all. And on the right panel, we see a similar depiction, but what's happening here is we're talking about much smaller vessels. Still around North Carolina, we see a little bit of movement, but not nearly the movement that we're seeing with those larger vessels depicted on the left-hand side. What this tells us is larger vessels are traveling further, but that depends on whether you're based out of Maine or whether you're based out of North Carolina. They also dug in further to try to figure out why is there this inconsistency between locations. And what they found is that the larger vessels that were targeting multiple species, so we say that had a diverse catch portfolio, they stayed put. But in contrast, vessels that had a low diversity of catch, so really targeting one specific species, they were often willing to really move significant distances to chase that one species. So it appears that catch diversity and high mobility may buffer fishing communities from the effects of environmental change. Especially in times of rapid change, it seems like having a diverse portfolio, meaning you target multiple different species, and also you have the ability to move long distances because you have a larger vessel. Those types of characteristics can help a fisher adapt to these changes. Community traits also influence how fishers respond to changing resource availability. Fishing communities are incredibly diverse around the world. One example of a smaller scale fishing community would be Owl's Head, Maine, not too far from where I grew up. And it's a community where if you don't fish, your neighbor probably does fish. The population is just around 2,000 and the median age in this community is 52 years. And set that in contrast to Boston, Massachusetts, where it's another really economically important port in the Northeast United States, but it's very easy to live and work and live your life in Boston and not actually know anyone who fishes. The population is 700,000 and the median age is 32 years. A port like Owl's Head in Maine exhibits high community reliance on fishing. There aren't a lot of other opportunities to make a living if you don't want to move to a new place. And then that's in stark contrast to what might happen in Boston, where if because of climate change, the marine landscape is changing tremendously, there are a number of other economic sectors that you could participate in outside of fishing. We might expect fishers in Owl's Head to want to stay in the fishing industry because of the lack of other opportunities, but also because of the cultural importance of fishing in a town like that. While in contrast, we might expect fishers in Boston to be more likely to just leave the industry completely. We still don't know the answers to a lot of these questions, but we're working closely with anthropologists and social scientists to better understand this type of decision making. But what about the response to range shifts by fishing managers and heads of states and military leaders? To continue to understand the complexities of decision making regarding marine resources, let's take a look quickly at how marine species see the planet. Marine species see the planet like this. They don't see boundaries. They might see biogeographical barriers like land or islands or particularly deep areas, particularly shallow areas, but they're limited by their mobility. They aren't limited by political boundaries. But this is how we see the Earth, quite a bit differently than these species that are actually shifting their ranges see the Earth. We see the Earth as a mosaic of political, economic, and social boundaries, both on land and also in the ocean. And the reason this map looks a little bloated, to say the least, is because it reflects not only the economic territory associated with nations on land, but also the economic territory associated with these nations in the water. And the term that we use for the area beyond land that nations can claim jurisdiction of is the exclusive economic zone. And that extends 200 nautical miles off of a country's coast. This exclusive economic zone, which I'll call EEZ, was not actually established until relatively recently with the United Nations Conference on the Law of the Sea in 1982. And so while a lot of countries and nations and leaders have decided to play by the rules, inevitably, if a country has centuries of experience fishing, they're then told that their fishing has to be restricted to this exclusive economic zone. The conversations and the deliberations between these nations in terms of who owns rights to the ocean become quite convoluted, quite complex, and sometimes slightly violent. And ocean governance is continuing to get more complicated as species continue to maximize their fitness by shifting their ranges, and therefore accidentally crossing these international boundaries. This graphic here shows the number of transboundary species, so species that will cross from one economic zone to another, that we expect to newly come to be by 2100. The areas highlighted in red are areas that we expect to have to deal with a large number of these new transboundary stocks in the future. And returning to an earlier graphic we looked at, there's no coincidence that when we look at this map of changing ocean temperature, it overlaps well with these areas that we expect to gain these complicated, wicked to manage transboundary stocks. Areas like the Arctic, areas like the North Atlantic, areas like the South China Sea and the Sea of Japan. And unfortunately, there are already a number of climate-related conflicts that have arisen, even between typically friendly nations. One example that's quite close to home for you all is that of the mackerel wars, which have persisted for over 10 years now between Iceland, the Faroe Islands on one side, and the UK and the EU, and also Norway on the other side. Atlantic mackerel, you can see the beauties here in the Guardian article. They're a relatively small, fatty schooling fish that have historically been caught off the coast of Europe for centuries. And it's among the UK's key exports. But about a decade ago, because of warming temperatures, mackerel started to move north, away from the UK up into Iceland, and also the Faroe Islands. New economic opportunity. Iceland and the Faroe Islands were obviously both really excited by this and started catching the mackerel that were in their waters. But obviously, the UK wants to maintain their ownership over the stock that they have a lot of cultural and also economic stake in. So this conflict between many of these relatively seemingly friendly nations is still ongoing. And it's led to unsustainable overfishing, trade embargoes, and boat blockades. And it also played a role in Iceland actually withdrawing its application to join the EU. This is an example of conflict arising among relatively friendly nations, but there are also a lot of examples arising between slightly less historically friendly nations. Conflicts exist in plentiful numbers off the coast of Asia and specifically in the South China Sea. And despite these internationally agreed upon exclusive economic zones, China continues to claim more than 80% of the South China Sea. The area claimed by China is highlighted in this red dotted line here, spanning almost the entirety of the South China Sea. But if you look at the blue dotted lines, those are the internationally agreed upon exclusive economic zones. There's a lot of overlap in these conflicting territorial claims, including Vietnam, Indonesia, Malaysia, Brunei, and the Philippines. And China does not just back this claim with talk, but also backs this territorial claim with Navy and Coast Guard vessels, making it really hard for these more developing nations to have access and support themselves by accessing these resources that by international law are supposed to be theirs. And it's led to conflict between China and these other nations, but it's also led to conflict between these developing nations as well. On the right-hand side is just one photo of so many that could be taken, showing Indonesian authorities sinking an impounded Vietnamese fishing boat just a few years ago. And this is just one instance of conflict that's literally happening day and night in many regions across the globe, but especially in the South China Sea. And at the same time, it's important to note that this area actually boasts some of the most incredible marine diversity in the world. And we expect, as a result of climate change, for the distribution of many important commercial species to be changing. And so this conflict that already exists, unfortunately, we expect to persist and even accelerate and intensify going into the future. And these types of conflicts have consequences for human life, for food insecurity, for conflict to arise in non-fishing sectors, and also often lead to severe overfishing of these populations. But the good news is that we can prepare for these range shifts, and there are steps that nations should be taking in order to anticipate future range shifts and this rise in transboundary stocks. Some important measures include planning ahead for cooperative management, making the goals and responsibilities of each nation clear before the transboundary stock is actually in existence. Also, finding unique ways to incentivize cooperation, possibly through tying in non-fishing resources. Regularly updating allocations across different nations based on recent population assessments of these different species of fish. And also a more kind of like novel out of the box idea is to develop fisheries permits that are tradable across political boundaries. There are some really awesome examples of success stories for groups that are thinking forward into the future and how to effectively and fairly manage these transboundary stocks. And a few examples include the Pacific Salmon Commission between Canada and the United States, the Commission for the Conservation of Antarctic Marine Living Resources among multiple nations in the Southern Oceans, and also Joint Fish, which is a commission between Russian and Norwegian fisheries. And the last thing I want to end on is just saying that I've focused on the conflicts that arise when fish do not follow the boundaries that we have instated. But that story is not unique to fish. There are so many natural resources that are moving in space as a result of climate change that we have not yet built the infrastructure for how to equitably manage into the future. Just one example are freshwater resources, which are changing in distribution and overall decreasing worldwide. We don't yet have a good sense of how to manage these resources either moving into the future, but we can likely use similar techniques in terms of incentivizing cooperation and also making sure that infrastructure is set up before it becomes more of a problem. And I know we're coming to the end of time, so I'm just going to end by reminding you all of the fish's experience and how it intersects with our own experiences. Marine organisms, from fish to lobsters to squid, they have been in our oceans for literally millions of years. They are resilient and they will absolutely adapt, even if they're living in new places or looking different than they did in the past. But the more important question to us is how we will adapt. And with that, I will finish up by thanking Eli for the invitation and you all for listening today. And just a quick thank you to my funding sources and also my data sources and the wonderful group of scientists that I get to work with every day at Rutgers. And happy to answer any questions that anyone has if we have time.
Thanks so much, Zoe. We are a little tight on time, but I think we can, nearing 3 o'clock on a Friday afternoon here, we can. There is space for questions if people have time. Mary's clapping. I hadn't seen that emoji happen. So there we have space for questions, 1 or 2, and if people have them. Mary, please go ahead.
I'd just like to say thanks for a really super talk, Zoe. I think you should make this for the BBC. No, seriously, it was really super. I thoroughly enjoyed it. I do have to go in a few minutes, so I'm going to barge in and ask a question or so. One of the things that happens with species moving around is invasive species. And we just had a discussion in our climate change class this morning about where the line is between invasive species and species that are just moving in the way that you described. And sometimes these things might overlap. And a species gets into an ecosystem where it's really changing things. Has that been encountered in the kind of work you're looking at?
Well, first, thank you so much. You're so kind. But thank you. Such a good question. And I have also struggled with that conflict, it seems, we have these species that we label invasive, but in all reality, in response to climate change, you could claim that all species are becoming invasive. And I think the way that I have thought about it that's helped me is thinking there is this incredible literature about invasion ecology. And because a lot of these species that humans have physically moved into these new novel environments have really altered what's happening in that ecosystem, I've actually pulled so much from that literature in my own work focusing on native range shifts. So I think what I would say is there's not a good way to differentiate those two processes. And I think the way that happens most often is people say, well, if the human physically carries an organism to a new place, and I think that's probably the easiest way to define a proper invasive species. But I think the better way to think about it is to pull all of the things that we've learned about invasive species and how they impact communities and apply that to these native range shifts that we're seeing.
Yeah, because you talked about traits and trait lists, and I think that might differentiate them. Is there any chat going on? Or actually, I'm going to say thank you very much and leave with a question. I'm going to go away because I have another meeting, but I'll catch up the recording. I'd love to know a bit more about the deoxygenation that's going on and how serious people think that is. But seriously, I'm going to say thanks very much and bye because I have to go off. But thank you.
Thank you so much for coming and for your great questions. I will touch upon the oxygen issue. And in a lot of ways, oxygen is temperature's less understood cousin hiding in the corner. As a consequence of temperature change in the ocean overall has less oxygen. And that's because just by the properties of water when it's cooler is chemically able to hold in more oxygen, while water when it's warmer cannot hold as much oxygen in. So on one level, that's what we see happening. So overall, the global ocean has less oxygen. But at the same time, what we see happening is in some regions, depending on the oceanography of that region, or alternatively, depending on the different types of nutrient influxes from land, that process is being accelerated. And so areas like the Baltic Sea, areas like the Gulf of Mexico off the coast of the United States, or the California current system in the Northern Pacific, those are areas where this decline in oxygen that we're seeing worldwide is really being amplified and accelerated.
Time for one more, if anybody has one.
No.
Yeah. Yes, please go ahead.
You go, Sarah, or I go?
No, you can go. It's all right.
Oh, we can ask both. I think so. It will be a problem. My question is actually related to how, because you spoke about fisheries and how they may affect. Did you went like a little bit further to the industrial fisheries and how they may affect beyond, because they literally like, it's not like they study the specific ecosystem of this fish and they go and scrap all that beyond, going beyond climate, of course.
I'm so sorry. Do you mind just repeating that one more time?
Because for example, in my country, there's like a latent discussion about how fisheries, like local fisheries, may compete against industrial fisheries. They literally have bigger boats, so they may affect more the ecosystems. So there's nothing to fish at the end of the day.
Yes, absolutely. You bring up a really important point that I didn't get to highlight as much as I would have liked to, which is this question of equity. And as we have fish changing where they live, but then we also have immense variety in the type of fishing vessel that exists. And so if you have these larger fishing vessels, which can move further from their home port and they catch more fish, they're inevitably going to have a much bigger impact than these smaller scale fishing communities where fish are kind of like synonymous with survival and livelihoods. And there's, unfortunately, this is just a rampant problem that's happening in so many areas. And I think one example I highlighted is what's happening in the South China Sea, where these industrial fishing vessels from China are outcompeting these smaller scale fishing vessels from a number of other countries in that area. Unfortunately, I think with climate change, that is only going to amplify that inequity between those two groups. But I know that there are a lot of groups, especially as a part of the United Nations, who are trying to think of innovative ways to protect the rights and livelihoods of those smaller island communities and coastal communities as well. But yeah, it's a challenging problem that we face on many levels and don't have a good solution for at this point.
Sarah, did you want to ask or close us off? Did you want to ask one more?
I'll try and keep it quick. Just wondering, since you work in kind of the intersection between marine ecology and more sort of anthropogenic side, do you have any sort of best practices for folks like me who are focused on how fish are going to move with climate change, how to best sort of disseminate that to the folks who need that information?
It's a really great question. And I think it's a very cliche answer, but I think in my work, what I've found to be the most helpful is when it's possible, pulling in those stakeholders, whether they be managers or whether they be fishers, as early in the process as possible. I think too often we come up with a question, get our answer, and then we present it out to these groups. But when those groups are a part of that process from the development of your scientific question, not only do I end up asking better questions, they also end up being more helpful for those people who are hopefully going to benefit from my science in the long run. So I'd say the biggest piece of advice is just pulling in stakeholders at more steps of your process. It does slow things down, but it often leads to better science in the end.
That's great. Thank you very much. And excellent talk as well. Really enjoyed it.
was an excellent talk. Thank you so much, Zoe, for your time today and for joining us for this. And I'm looking forward to posting this with the other contributions to the seminar series. But it's really exciting to get marine spatial ecology, especially in this discourse. And I always look forward to whatever's coming out of your lab. So it's always it's fun to watch.
You're so kind. Thank you so much for having me. Thank you for the great questions. Also, if anyone, I know I went a little longer than I had hoped to. So Eli, feel free to share my email if anyone wants to get in touch or continue the conversation.
That's great. Thank you, Zoe. We'll catch you soon.
Thank you, everyone. Stay healthy.